Therefore, the next line is equivalent to the one above it because I've made that substitution.
So it wouldn't imply it would just be straight equal.
Straight equal.
Right.
Yep. Now, if you put implication, it wouldn't ruin everything, all right? All right, good? Understand? All right, last one, secant cubed. Yes?
So my understanding is you knew that the derivative of secant x plus tan x was that because you took derivatives of each of them separately?
Yes.
Okay.
Yep. Yeah, because on the bottom it's addition, right? So you take a derivative of each one individually.
Okay.
And it just so happens that if you do that, that's what the top is. And that all worked out because somebody figured out that's what we need to do, right? Because remember, the original integral was just secant. That's all it was, right? And then we made it this big, ugly, complicated looking thing, but it turned out that that was something we could handle. It's a weird problem.
So is U substitution historical for integration by parts?
No, they're different techniques.
Okay.
Yeah.
Right.
For this one, I'm just going to get rid of this because I don't need it up here. It's just taking up space. All right, integral secant cubed x dx, last one. And then we're going to move into the second part of this section. So for this problem, there's no magic that someone had to sit there and struggle with forever, okay? This one can be done with integration by parts. And so what we can do is make our table over here for integration by parts. And I'm gonna peel this apart into two pieces. I'm gonna go secant x times secant squared x dx. Right, that's what secant cubed is. And then if I'm looking at this with integration by parts, I know that that's the derivative of something, isn't it? That's the derivative of what? Yeah. Tangent, right? So this can be my dv, right? That can be my dv over there because when I do integration by parts, I'm going to wind up integrating that, and it'll become tangent in my table, right? This will become dv, secant squared x dx. And then that forces me, if I'm doing integration by parts, to let this be the u, right? And then I'll have to differentiate secant. So I can differentiate secant, that's okay. And I'm just going to hope for the best here, okay? So the derivative of secant x is secant x tangent x, right? dx. And then the antiderivative of secant squared was tangent x. Right? Any questions? Equals ultraviolet minus voodoo. So ultraviolet, are these two multiplied together? So secant x tangent x minus the integral. Now voodoo, this is not looking too nice, is it? These together, right? Those together don't look very good. But let's put them together. So if I do that, how many tangents will I have? Two factors, so tangent squared. And I only have one factor of secant, and I'll have my dx. And that's my new integral, right? That's the new integral. And I think you could argue that that integral is not much better than the original one, but maybe we can do something with this. So we look at it enough. What about our sheets? Do our sheets tell us anything about this? Or,
Break up what the tangent?
Yeah, like should we peel off a tangent? Let's see, what did this say? If we have, going here where we have secants and tangents, right? If we have secants and tangents, it says if you have tangent with secant and the secant is even, right? If the power on the secant is even, then we'll do that. And then the other one says, if the power on the what is odd? The power on the tangent is odd. Do we have that here? No. We have, this is not even power, and that's not odd power. So I can't, the methods I have won't work for this. Right? Yes?
Can we do U sub and then use identities for tangent squared?
What U sub would you want to make?
So first I would take the tangent squared squared and change it into. Secant squared minus 1.
Okay, so you want to do Pythagorean identity on this,
Yeah.
and then look maybe to do a U sub or something. I'm okay with doing that. That's not, I thought you meant let's just do a U sub right here. Now, you want to use Pythagorean? I'm willing to go down that road.
So
Any other
that's
ideas?
the harder road?
No, it's actually the right road, but there could be something else that someone sees they want to do, right?
Integration by parts.
Okay, if you did integration by parts, what would you choose for your U and your dV on your new table?
My u would be tangent and my dv would be tangent at secant x.
Okay, let me write this down.
Yeah.
Okay, so what's happening here is Andy is saying is that instead of writing this, right, we're going to separate the tangents and do one tangent here and then do the other tangent with the secant, and you're seeing that this is the derivative of secant, yes? So that's going to be your dV in your new table, and that's going to be your U. Everyone see that? Do you have a comment?
Well, I was going to say probably rewrite tangent square x as sine square x over cosine.
So you could go to sine and cosine here as well. But let me stay on one road at a time here, just because I don't want to go too. But you could try that. You could try that as well. Let me see here. So we're going to do dV is the secant x, tangent x dx. And then the u would be, what, tan x? Like that? Y'all see this? Now let's finish the table. If we do this, the derivative of this, derivative of u is secant squared x dx. And then if we integrate here, we get what? What's the antiderivative of this? Just secant x. And we're gonna actually have a problem here now. Let me write it down. I want to go all the way with this so you can see. Just remember this line because I'm going to come back to it, okay? Secant x, tangent x, right? Minus this integral is going to become ultraviolet minus voodoo, right? So minus, oh wait, hold on. This may go. Hold on, let me just finish it. Hold on. Ultraviolet, so secant x, tangent x, right? Ultraviolet, minus the integral of voodoo. What's the integral of voodoo? Secant cubed, which is the original problem, isn't it? So maybe this is going to be that rabbit out of the hat problem where we can move it to the other side. We've got to make sure that the signs work out, though. The signs have to work out, right? You can't just assume now everything's going to work perfectly, right? Y'all with me on this? Everybody's good?
Yeah.
Okay, I'm going to keep going. I'm going to do it up here. Let me see where we are. The original problem, right? The original problem is equal to this line, secant x, tangent x, right? And then I'm going to distribute this through here to here. What do you get? Minus secant x, tangent x, right? And then plus what? Secant cubed x dx, right? And do you see what we just did? These cancel. And what are you saying? Secant cubed x dx. This integral is equal to itself. Thank you, it is. But I haven't solved anything, right? Right? It's not a solution. I've just shown that the original integral is equal to the original integral. So why did it do that? There's a reason why it did that. The integration by parts that we did here basically reversed the integration by parts we did the first time. Remember how the integration by parts, what it does is it creates a new formula where you've switched the derivatives. You've switched what's being differentiated and what's being integrated. You switch it. If you do that same integration by parts on that integral and you switch the two functions, you will go back to where you came from, which is exactly what we did. And the reason I wanted to do this because I wanted everyone to see that that's what happens.
So is that wrong?
Well, yeah, because we haven't solved the problem. Remember, we need an answer. We want to know what the antiderivative of this is, right? Right? This is like me saying x is equal to x. But that doesn't tell you what x is, right? So I don't, yeah. This is almost like doing this. This is almost like saying, I don't know. Nah, I just leave it alone. Okay. Yes?
So, like, it would pretty much do that no matter what for any and all integration by parts if you were to take the same thing.
Yep, it'll do every single integration by parts you ever do. If you basically do it a second time and reverse things, it'll go right back to where it came from. And you'll be basically back where you started. Yes?
So when we first started this class, we said like, you know, like one of these 5 or whatever integration techniques.
Yeah.
This is one of them where you can kind of identify like, hey, this is not a good one, let's go down, let's try something else.
Say that again, because I want to understand what you're.
That was just the wrong path.
Yeah, that was just, we just went down the wrong path. There's no harm in that, no foul in that. It's, you know, it is what it is, right? Well, but you now know that that's possible, right? And if you were to do, I promise you, if you went down that path a couple of times, you'd start to realize, I better not go that way anymore. You're going to start to see why you shouldn't go that way. It will never work out for you. Like it won't ever work out if you just undo what you just did. It's like adding 2 to both sides of an equation, then subtracting 2. It's like you just did something, then you undid it.
So we're starting back from.
We're starting from the line that we had here where we had tangent squared x secant x dx. Now there was also a comment to go with sine and cosine, right? I do not think it'll go easily that way though. It might, but I don't think it will. So I'm going to go with the suggestion to turn this in using Pythagorean, right? We have the Pythagorean identity that I put up on the board earlier today, in the very beginning, that we should know from pre-cal, right? One of the Pythagorean identities. And what I'm going to do is I'm going to solve it for tangent squared. So I'm going to turn that into secant squared minus 1, right? So now this becomes secant x tangent x minus integral, okay, this in parentheses is secant squared x minus 1, and then times secant x dx. Right? Distribute the secant through, yes?
Can you do me a favor? And
Maybe.
Visualize the Pythagorean identity so I can remember it.
Visualize it.
Yeah, like how's it drawn out?
Unit circle, go with theta instead of x. The x coordinate is always cosine theta. The y coordinate is always sine theta. You okay with that? Right triangle, the x coordinate is cosine theta. The y coordinate is sine theta. And now a squared plus b squared is c squared. This is 1, right? So now you have this identity, which is not the one you asked me about, right? Okay, once you have that identity, if you believe that's true, then take this and divide everything right now by cosine squared. Okay? So divide this by cosine squared theta, divide that by cosine squared theta, and divide that by cosine squared theta, and you will get tangent squared theta plus 1 equals 1 over cosine is secant, but squared is secant squared. There's your identity. That's the way you get that identity. All you do is take the Pythagorean and divide everything by cosine squared. And there's a third identity that you get if you take all of that and divide by sine squared.
And you can always derive it.
You could always derive it. That's right. If you know this, you could always derive the other two. Exactly.
And knowing what again though? Like the sine squared theta plus cosine squared theta equals 1. Okay.
That's what you have to know. Yeah. Okay, distribute, let's distribute. Can we do this for a second? Can we just like, no, I'll just write the next line. I'm just gonna get a little lazy there, but I'll just continue. So this is equal to secant x, tangent x, right, minus the integral. Now I'm gonna have 2 pieces in here when I distribute through. Secant cubed x, crap, that's the integral I'm looking for, isn't it? And then secant x and then dx. So Yeah, it looks worse now. Yeah, we've added a minus secant x. But see, when we did it a second ago, what happened was a bunch of stuff canceled, and we had the integral on both sides, right? When we were like, oh, great, it's the same thing, great. We didn't get anywhere, right? This is not going to happen this time. Let me show you why. Watch this. Okay, so this is minus, right? Minus. I'm going to split this into two integrals. So it becomes, I can do that, right? Two antiderivatives because there's subtraction between them. And this will become a plus on this integral because I have a double negative, right? I have the minus here and the minus here, so it becomes that, yeah?
Yeah.
Do you know the antiderivative of this? We just proved it, didn't we? Natural log of the absolute value of secant x plus tangent x. So I can handle that, can't I? Yes? And this is the integral I'm looking for, right? But do you see how it's being subtracted? That means I can add it to both sides of the equation. That's not what happened in the previous way. So let me write my next line. Here's where we are. This equals, I'm going back to the original problem. This equals this, secant x tangent x, okay, minus the integral of secant cubed x dx, and then plus the natural log of the absolute value of secant x plus tangent x. And then I'm going to have a plus c, right? I'm going to have plus c at some point, so I'm going to put it here. Yes?
Well, my question is like, you had the integral of secant cube x before the secant x. Like, I know it has to do with order operation, but when you do that one first and do that.
Oh, absolutely. Oh, yeah, absolutely. I just left it where it was, that's all. And it's really not going to matter because on my next line, I'm going to add this integral and then add the integral here, and it's going to go away on the right-hand side. Yes?
Why did you do plus secant?
Because I erased it. No, well,
It's still up
Because it's going to be.
no.
You can still add it.
Here's where we had this, right? We had this. That's what we had. Do you see that line? And I made this go into two integrals. But do you see that minus? This minus is impacting the entire expression. So that minus has to go to here too. All right, now I'm going to add it. So I add this integral on both sides. Add the integral over here. They go away. And now I have two of them, don't I?
Yeah.
So I have two of them over here. Two of these integrals that I'm looking for is equal to secant x tangent x plus natural log of secant x plus tangent x plus some constant, right? I'm just going to keep that there. One more step. Divide everything by 2. So I'll put a half in front here, and I'll put a half in front there, and get rid of the 2 over here. And I don't need to take half of c, because it's still a constant. There it is. Yes.
It works if we did a u substitution on here, right, too?
Which, for what?
For
What part?
when you have the secant squared minus 1 times secant x, because the derivative of secant squared minus 1 is 2 secant.
Hold on.
x.
You said back when we were at secant squared x minus 1 secant x dx, that a u substitution would have worked?
No, it wouldn't be this. Never mind.
Yeah. But what were you thinking? Because I think it's worth us talking about.
The 2 times secant x would be helpful, but then you have to take the derivative of the inside second.
Gotcha. Chain rule would mess it up, right?
What is the symbol next to the secant?
I killed off the 2 that was here. There was a 2 here. I divided everything by 2. So it's gone now. It's a 1.
So is that like, is that in other math classes or is
What?
Or is that shorthand?
This thing?
Yeah.
Oh, that's just me saying shit, it's gone. Like, yeah, it's not.
Make up our own symbols. Sometimes.
Yeah, no, I'm just saying it's gone. That's all I'm saying.
Right.
Yeah, if you want me to be precise, I divided by 2, and now that becomes a 1.
So,
Oh,
would this problem have been possible if you hadn't have broken it into 2 different integrals, or was that like?
I needed that because I needed to be able to add that secant cubed x dx. I needed to add that integral on both sides. But that breaking apart wouldn't have happened had we not did the Pythagorean identity, which changed the tangent squared over to the secant squared x minus 1, right? So, yeah, a lot of trial and error and persistence. Didn't I say that, persistence? Yes. Uh-huh.
So what if you would, instead of doing antiderivative and then adding the secant cubed on both sides,
Mm-hmm.
what if you would add the secant cubed on both sides and then an antiderivative? Would the one half would change the answer? I was trying to visualize it, but I couldn't.
Well, we had the two different integrals. Are you saying before that? The step before?
Because we split it into two
Yep.
integrals, and then what if we had added to both sides the secant cubed before we did the antiderivative here?
Yeah, but then you'd still need to take that antiderivative, wouldn't
It
you?
would end up the same way.
Yeah, because you would have two of these integrals equals all that, and you'd still have that integral over there, and then you'd find the antiderivative and then divide by 2.
Mm-hmm.
Yeah. If you brought that 2 over before you did the integration, it would just be a 1/2 in front of the integral, right? Yeah. Yes, sir.
Can you only break up the integrals if there's
Plus or minus. Yep. You have to have some or, addition or subtraction, right? Because if there's products, right, this is what started this whole mess, right? Like if we had this integral, right, there's multiplication here. We said Cal 2 would be really easy, if you could break that up into 2, like that, right? Because then that is just like 1/2 x squared, and this one, the antiderivative is sine, and then we just multiply. If that's the way it was, then shit,
What is that?
it's just, this is not okay.
Like, we can't use the product rule when we're integrating.
No, you can't. The whole idea is us trying to undo the product rule. That's what makes it so hard, right?
Yeah, true. It's like reverse foiling.
It's reverse product rule, which product rules, ugh. So, all right, we good? I understand you got to go get your hands dirty now in that section and work with those integrals and see how they go. 6.2. Well, 6.2, yeah.
This is kind of a weird question, but so.
Getting a lot of them today. No, I'm kidding.
So we as humans, when we do antiderivatives,
Mhm.
we have to try to find, we have to work with it and try these different methods that
Yep.
we taught ourselves. When a computer does it, what does it do?
So this is a good question. Your computer doesn't see it as functions like we do because remember I told you in this class, chapter 8, right, is sequences and series, right? That's an important chapter, vital chapter, because what it does is it tells us that if you take any function, there's a way that you can rewrite any function as an infinite polynomial. I'll give you a simple example. If you take the function e to the x, right? That function is exactly the same as 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus ... Now that goes forever. It's an infinite polynomial. This is called the Maclaurin series for e to the x. So in a computer, if I want to know what e to the second power is, you type that into your calculator. What your calculator does is replaces all these x's with 2's. Right? And then it stops at some point because the computer won't go forever, right? But a computer can do all the arithmetic operations extremely fast, right? Addition, subtraction, multiplication, division, right? Powers are just repeated multiplication. So if you ask a computer to do this computation and do this out like a million places, does that make sense? Like do this a million, it can do that like that, right? And it spits out some answer. Now if you don't believe that this is true, do e squared on your calculator and then try and do that on your calculator, and I bet you the answers will be close. And if you continue out further with this pattern, they'll be the same number eventually. So when you're asking a computer to do something like antiderivatives or derivatives, right? They're not looking at it the way we do. That's the way it sees it. And so think about that. See if this might blow your mind. What's the derivative of e to the x? Itself, right? So let's try that. If I take the derivative of this, according to what I've put up here, these should be the same thing, shouldn't they? Yeah. So what's the derivative of 1? 0. What's the derivative of x?
1.
Okay, now here we would have to use power rule, right? 2 comes out, cancels, and we get what? X. Here, the 3 comes out, and we get a half, right? So we get the x squared on top, but now it's over 2. And then the next one, the 4 comes out, reduces out to be 1/6, and we get x cubed over 6. And if we keep doing this forever, do y'all see that these are the same exact things?
Yeah.
This is the only function that does that, all right? This is the Maclaurin series for e to the x. Every series we have, or every function that you could ever come up with has a series. Here's the one for sine. Let me just think for a second. Okay. I'm going to use a different notation because it's easier. Do y'all know what that exclamation point stands for? It's factorial. We'll talk about this later. This means 3 times 2 times 1. This means 5 times 4 times 3 times 2 times 1. This means 7 times 6 times 5 times 4 times 3 times 2 times 1. You get the idea? No? That's what it is. So if you go to your calculator and you're in radian mode, and you type in sine of 2, your calculator puts a 2 here, 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 and cranks out a number. Right? And, go ahead, were you going to say something?
No.
Do y'all remember that in algebra, pre-cal, you're told that sine is an odd function?
Yeah. Oh, okay.
Look at all the powers on the x's. They're all odd, right? And you're told cosine is an even function? Well, guess what? Its Maclaurin series has nothing but even powers of x. In fact, that's the new definition of even and odd in this class, is that even means that its Maclaurin series has even powers. And that. So is e to the x even or odd? Neither. You don't have to be one or the other. You can be neither. It has both odd and even, right? Okay, we're going off. Let's get back on track. I know you have another question. Let me hear it. I'll decide if I want to go down that road or not.
So you said that computers don't use like functions like we do. They just like if it would take the antiderivative, it just plugs 2 in for x, right? But when you go to like math lab or one of those websites, like
Okay, so you're talking about something that's doing like symbolic manipulation, like algebraic, and giving you some function answer. It's following rules of differentiation, but it can learn an algorithm to do power rule, right? And bring a number down and do all that. So you know how we just did that with e to the x? If you differentiate on computer, it does the Maclaurin series, does the derivative, and then looks at that series and converts it back into a function. So it goes both ways. Does that make sense? Yeah. Okay. You ready to move into the second part of this section? Trigonometric substitution. Trig sub. I call it trig sub. What we just did was called trig integrals. Integrals involving trig functions. Now we're going to do something called trigonometric substitution. So by the name, we're going to be doing some sort of substitution, right? And it's going to involve some trig, all right? So to motivate this idea, let me, how do I want to do this? Every semester I try and do something different the way I approach this. I want us to look at there's going to be 3 cases that we're going to be looking for. Or I shouldn't say 3 cases. It's 3 forms, okay? There's 3 forms of integrals that we use this trig sub for, all right? The first form is when we see somewhere in the root, somewhere in the integral, we see the square root of some constant, I'm going to call a squared minus the variable squared. That's the first form. If we ever see an integral that involves that, we're going to be thinking trig sub. Let me give you some specific examples of this. Okay, examples would be this. Another one. I'll do x cubed. Those are 2 examples of where we would look at them and we would think hey, maybe we're going to use trig sub here. Because what we're seeing is some numbers squared minus the variable squared. Everyone see it, right?
Yeah.
3 squared minus x squared. 3 squared minus x squared. These integrals are different, aren't they? Right?
Yeah.
But this, I would be thinking, hey, trig sub might be, you know, I'm going to pull out the trig sub just in case I need it, right? That's the first form. The second form that we might see is that reversed. So you have to remember that when it comes to roots, you can't just pull out a negative, right? I can't factor a negative out of a root because that would give you an imaginary number. So you can't turn this into this by just pulling a negative out. Now, if the root wasn't there, there's a way you could pull a negative out and they'd look exactly the same. But under a root, you can't. So if we see something like this, we're going to be thinking trig sub. Examples of that would just be, you know, take these and reverse the order, right? Reverse the order. Do x squared. Let's do x squared minus 4 instead. And then let's do x squared, let's say, minus 3. Ooh. So on this one, that's this second form, isn't it?
Yeah.
What's a for us here?
4, 2, or 2.
A is 2, right? A is 2. This number right here is the a being squared. So here a would be 2. What would a be here? Square root of 3. Right? I mean, it's not a perfect square, right? 3 is not a perfect square. So a would have to be the square root of 3 here. But that's okay, because it's still just a number, right? And then the third and final form is x squared plus a squared under the root. And now this one, the order would not matter. You could have it the other way around, because addition, you can change it, right? And it doesn't change anything.
So that's probably like the most confusing.
Well, yeah, if you see plus, there's only one thing that can happen. If you see a minus, you have to know which one we're talking about, the first or the second, right?
C plus, the programming language?
Yeah, see, if you see plus, you're in business. All right. So all I've told you is that these are the types of integrals we're looking at, right? These are the types of integrals that are going to tell us maybe trig sub, right? So I haven't even told you what trig sub is yet, right? Just that this is what's going to like make the little light bulb go off. So do you think I would use trig sub here?
Yes.
Is it one of these forms?
Yes, the first one.
That one, right? So you're thinking trig sub?
Yeah.
Yeah?
Yep.
Or trig form.
Okay. What about basic u sub? Do you see something in its derivative?
Yeah.
Yes. Off by constant.
1 minus x squared. What's the derivative of 1 minus x squared? 2x. You're off by a constant. Do not do trig sub.
Wait, why?
Because this is basic u sub. If u is what's under the root, the derivative of that's right up there, but we're off by a constant.